In this video, I'm going to show you how to calculate the slope and y-intercept for a linear graph, but also calculate the uncertainty on those parameters. So how certain are we about the size of the slope? How certain are we about the y-intercept? First of all, I'm just going to pop in a graph here. Sometimes the Google Sheets can be a little frustrating to deal with. I'm going to put in a a scatter graph. The default is column. I'm going to add data for the x-axis. I'm going to highlight that speed data there and click OK. And I'm going to add the stopping distance for the next. So this has our speed as the x-axis and the stopping distance as the y variable. I'm also going to include under the series here a trend line. All right, so this is the trend line that you can also do in Plotly. And I'm going to include as a label the equation. So it is a slope of around 0.95 and a y-intercept of 1.33. Now this is just for reference because in Google Sheets we can't add error bars of a specific size. So you could go ahead and put in your y and x labels there. And you do that by editing the chart, customizing, and chart axis and titles. Maybe we'll just do the horizontal axis, which is our vertical axis title, which is stopping distance. And that's fine for now. The analysis here gives you a slope and y-intercept, but it doesn't give you how certain you are or what the uncertainty is about those two variables. So for that we use a particular function called linest. So just in some empty cell, say below your data, we can say equals linest, which is a function there, and it'll give you some hints. So in this first part here, we put in our known y data. So our y data is the stopping distance. So I'm just going to highlight the stopping distance without the title. Then I'm going to put a comma. And the next one we put in our known x data, which is our speed. And then I'm going to put a comma. Now the next two, you either put as false or true. So this next part here is asking you whether you want to calculate the y-intercept. And we do, so we're going to put true in that part there. And the last one is whether we want to return the statistics around those, which means get it to work out the uncertainty. So we're also going to say that is true. And then we just press enter and it spits out a whole bunch of stuff. Now, you can see, because of the matchup of values, that this value here is 0.95. So we're going to just write slope in here to remind us. And this one, 1.33, is our y-intercept. All this other stuff under here tells you something about the statistics of the analysis. But the one thing that we are interested in here is this second line. This is called the standard error of the least squares regression. So it's basically giving us an indication of how well we know this value of the slope. What we need to do here is take this value and multiply it by 2, and that will give us the uncertainty or the range with a 95% confidence, roughly, of that slope value. So we can say with 95% confidence that the slope value lies within the range of twice this on either side of the slope. So what that looks like is I'll write that down here. Our slope value equals 0.95 plus or minus twice this value, which is 0.318. Now, I'm going to write that there and then you may see what the problem is. I have now just going to put the units in here. This is actually seconds because it is how much the stopping distance increases per unit of speed. Don't worry about it too much. But you can see here that my uncertainty has too many significant figures. We need to bring this right down to one significant figure, because if we don't know the tenths unit, we're uncertain about that, then we're also uncertain about the hundredths and thousandths. So we're going to round this up just to be safe. Is 0.4, which means there's no point in quoting our slope to 2 decimal places if our uncertainty is only quoted to 1. So we will take this, should be up, rounded up in this case because it's 0.95. So what this does is actually takes it to 1.0. It's a little more complicated than I had been hoping to deal with, but we need to make sure our rounding is correct. Let's do the same with the y-intercept. Our y-intercept equals 1.33 plus or minus twice its standard error, which is 1.06, and the units of that are meters. But of course I'm going to take this right back to one significant figure. 1, I'm going to say 1 in this case. It's probably going against my rule. It was 1.06, but because it's such a small proportion, I'll just leave it at 1. And this will need to be taken back to 1, also rounded down. So in the 95% confidence, we can say that our y-intercept agrees with 0 in this case. What having these values means is that you can interpret your data, the physical representation, what that slope and y-intercept mean physically, and actually say whether it fits with what you're expecting and be quantitative about that comparison. So in this case, if you were expecting your y-intercept to be 0, then you could say at the outside that it is that your data does agree with that that expectation. Same if your slope, you're expecting it to be say 1.2, your slope would well within that 95% confidence interval agree with an expected value of 1.2. So that's how you can use Google Sheets. You can also use Microsoft Excel in the same way to calculate the uncertainty on your slope and y-intercept.